We are now in the position to talk about the most popular number in calculus, the number denoted by e. Where did it come from? And using what we've learned about sequences so far, what can we say about this number? Let us begin by examining my favorite sequence. If you've ever learned about how banks and money lenders compute compound interest, this sequence will look very familiar. There are two places where n appears in this sequence, in the exponent and in the denominator. The n in the denominator implies that the quantity inside the parentheses gets smaller and smaller, that is, closer and closer to 1 as n approaches infinity. However, the n in the exponent implies that the value of the entire term gets larger and larger as n approaches infinity. True enough, if we simply substitute the infinity symbol for n, we get a limit that is indeterminate. Now we ask, does the sequence converge? In other words, does the sequence have a limit as n approaches infinity? We now recall our fundamental axiom, and it says that if a sequence is bounded and increasing, then it converges. The question of convergence now becomes a question of boundedness and increasingness. Let us first see if it is bounded. In fact, yes, it is bounded. To prove that it is bounded, we start with the binomial expansion of each term in the sequence. We can easily compute the first two terms to be 1. And the remaining terms can be written more concisely using the summation notation. If we divide by the n minus k factorial in the denominator, the following term emerges. And if we count the number of factors in the numerator, we will learn that there are k factors. And likewise, the denominator has k factors, all of which is a value n. And thus, we can just assign one denominator for each numerator. And we can express it as the following product. Now we notice that each of these factors is less than the very first factor for all allowable k. And we also notice that 1 over k factorial can be expressed as this product of fractions. And because 1/2 is greater than each of these fractions, we can say that 1 over k factorial is definitely less than 1/2 to the k. And combining these two facts that we know, we can conclude that the terms in the sequence will have a value less than this. And then we now only need to apply the limit to both sides of the inequality. Taking the limit of both sides as n approaches infinity, we see that the limit a is less than 3. We note that this term is an infinite geometric series with 1/2 as the first term and with a common ratio of 1/2. So we can easily evaluate it. And thus, this sequence is bounded and it cannot exceed the value 3. Now let us explain the proof that this sequence is increasing. Let us take this expression from the previous slide. If we add 1 to the denominators in each of these factors, these fractions become smaller in value. And so this whole product becomes larger. And so the next step is just to add one more positive term for k equals n plus 1. And we obtain a yet larger expression. And this larger expression actually equals a sub n plus 1. You can easily check that. If you substitute n plus 1 to n here, we will get this very expression. And therefore, we say that a sub n is less than a sub n plus 1. And this is the very definition of an increasing sequence. We've now learned that a sub n is both bounded and increasing, and therefore it converges. Mathematicians call this limit the number e. Later on, we will see how this number e easily becomes the most important number in all of calculus. And although we have not computed the actual value of e, we have learned from the previous slide that this sequence is bounded above and that e is less than 3. And if we use our calculators, we get a value that is around 2.7. And although we won't prove it here, we note that e is an irrational number. We now try to solve a related limit. The only difference from the previous limit is the minus sign here. And we will attempt to find this limit by purely manipulating the expression. And my goal is to make it look very similar to the previous limit. So the first step is to consolidate the inner expression into a single fraction. And so we have the limit as n approaches infinity of n minus 1 over n raised to the n. And the next thing I'm going to do is to flip the numerator and the denominator of this expression so that it would look like the limit as n approaches infinity of n over n minus 1. And because I flipped the numerator and the denominator, I have to add an additional -1 here. And so these two expressions will be equivalent. And now I'm just going to add a -1 and add a +1 here. And then the new limit looks like this: 1 plus 1 over n minus 1. And we have a -n as the exponent. Now, the next step is to realize that in our previous limit, we did not have a negative sign here. So that's very easy to correct. We just transform this into a quotient that looks like this. We have a 1 in the numerator and a 1 plus 1 over n minus 1 raised to the n in the denominator. Now it looks very much like the limit for e. The only remaining part that we haven't added is the -1 here. And so we add the -1, but we don't want to change the value, so we also add a 1 here, and we get the following expression: 1 over 1 plus 1 over n minus 1 raised to the n minus 1 times, so we just separate the 1 here, and that's just 1 plus 1 over n minus 1. And now this is looking very good for us. Now we just need to change the limit from n into n minus 1. And we know that as n approaches infinity, we know that n minus 1 approaches infinity. And so we can replace this limit with the following: limit as n minus 1 approaches infinity of 1 over 1 plus 1 over n minus 1 raised to the n minus 1 times 1 plus 1 over n minus 1. And now we can apply the arithmetic operations on limits. And this is easy to do for the numerator because it's just a constant. And for the denominator, we can simply distribute the limit as if it was a multiplication operation. And now we have 3 limits to compute. This limit is just 1. This limit is also a common limit, and we know that this term here goes to 0, and so this is just 1 as well. And lastly, this limit looks very much like the limit that defines e. And in fact, it's actually the same limit. If you look at the form, we have an n minus 1 here, an n minus 1 here, and an n minus 1 and here. And so this is actually equal to e. And so we now know that this limit is 1 over e, or simply e raised to the minus 1. Now the next limit is not very difficult to compute because we already know the previous limits. The first term is to distribute the exponent so that we will be computing for the following limit. And now we can just apply multiplication of limits. And you can see that this is a very easy limit to evaluate now, because we know that this first limit is e, and the second limit is e to the minus 1. And so the entire limit is just 1. In this video, we've used the fundamental axiom to show that this sequence converges because it is both increasing and bounded. We have shown that this number, which mathematicians often refer to as e, is bounded above by the number 3. And so it can never go greater than 3. And we have also shown that by using this limit, it is easy to compute these two limits.